mass spring system as a simple harmonic oscillator. Simple harmonic oscillators are systems that oscillate with simple harmonic motion. Simple harmonic oscillator are two types: mass on a spring and pendulum. We're going to look at mass on a spring. If we have a mass M attached to a spring, and then you display the mass from its equilibrium, so this is the equilibrium here, and displays it by X to a new position, two forces are acting on this mass when you display it. One, you got the pulling force, so the force that you apply to pull it, so that's a pulling force. And then you got the force that is trying to restore it back into equilibrium, so the force for restoration. So this is restoring force. The restoring force, these are the two forces that we're going to consider in this situation. To consider those two forces, the restoring force F is going to be directly proportional to the extension X. It will be directly proportional to the extension X, but it's also in the opposite direction of X, so it's going to be minus. Because as you pull it and generate the displacement X, you are going to be experiencing the restoration to try and pull it back to its equilibrium. So that will be the minus. So now, if we transform that into equation, that's an expression, proportionality expression. So if we transform that into equation, FR is going to be equal to minus KX, where K is the spring constant. So that would be the spring constant here. And we could actually write K to be F over X, or minus if you like, and then the unit for that is going to be newtons over meters. So the spring constant has a unit of newtons per meter. That will be the spring constant. So K is a spring constant. Right, so that's a force that is trying to restore it back, hence restoring force. So that FR is a restoring force. And the pulling force, this FP, is another force that's acting on it. So that pulling force is basically, so let's just call it pulling, because you're pulling the mass, pulling force, so FP, and that will experience F equals MA. Because this is going through simple harmonic motion, right? Because it's going through simple harmonic motion, so let's just say FP there. Now what we're going to have is we're going to have the FR will be equal to FP, but FR is minus KX, and that should be equal to MA. But the A, we know what A is. A is the minus omega squared X, because that's what A is. A is minus, so that's acceleration of a simple harmonic motion, minus omega squared X. And we know what X is, that's the X displacement. So now, but we also know what omega is. Omega is basically 2 pi F. And so if we put it there, so we're going to have the pulling force Fp to be equal to minus 2 pi F squared X. And so that is what that will be equal to. So if we then, so that's omega times m, the mass. So we're going to get the Fp to be equal to minus m 2 pi f squared x. And so if we put that here, we're going to get minus kx equals minus m 2 pi f squared x. As you can see, the x will cancel out and the minus will cancel out. So what we can do is divide both sides by m. So we're going to get k over m equals 2 pi f squared. And in that case, I need to square root both sides, and that will give, let's just put it here, k over m square root equals 2 pi f. So that's the formula we're going to get. Now to find the frequency here, so if I rearrange this, I can get the frequency. So that's the frequency will be f equals, divide both sides by 2 pi, 1 over 2 pi, yes, root k over m. So the frequency has a relationship with the spring constant and the mass. The frequency f, if I write it here, f is directly proportional to root k, and f is inversely proportional to 1 over root m. So that's the relationship of the frequency with the spring constant and the frequency with the mass. And so that's the new formula that we need to recognize with the frequency here. And we can transform the formula for the frequency to period, because we know that frequency, so if I just write it here, we know that f is 1 over period. Period is the period of oscillation, time to complete one oscillation, and that's in seconds. So now I can then replace, it's a reciprocal of f. So period is 1 over f. That's a reciprocal of f, which means I'm going to have to invert that. So it's going to be 2 pi, and I have to invert this one as well, because 1 over, and root of m over k. So that's what the period would be. So the period would be, if I write it here now, so t equals 2 pi root m over k. So that is the period of oscillation. Period is measured in seconds. So that will be t is the period in seconds. So that's the period of oscillation in seconds. So that's the frequency derivation, and that's the period of oscillation in seconds for a mass on a spring.